Okay, great. Let's get started. This is my okay, great. So we are going to talk about the phase plane, and we would like to analyze the stability around 0, 0. This is, as I said, is important. So it's better we can analyze that without literally solving this system of ODEs, as we did in the first order. So in the first order, we didn't solve this ODE, and what we did is we using phase line pictures, and we draw the function of y prime as a function of y, and I want to see how this function cross when y equal to 0. And we can analyze these kind of what is called fixed point, and we can analyze the stability. So we want to apply exact same thing on this 2D systems. But turns out this is 2D, and as you can see, this is not as easy as we have in 1D. But hopefully we can get it. Okay, so this is the function that you see in the YouTube video, and we can easily transform into this kind of matrix form. As you can see, this is a constant matrix. Then we basically plug in the ansatz, and then we transform this problem into a matrix eigenvalue problems. The ansatz is like that. And you plug in, and what you get is, I'm basically trying to solve the eigenvalue problems. And after that, and we were solving this matrix, which is lambda equal to 3. And sorry, the first eigenvalue is 3, and the second eigenvalue is -1. And this is eigenvectors. And after that, we can write down the solutions for this ODEs. It will be something like x of t of c1 1 to exponential of 3t plus c2 of 1 minus t, c2 1 minus 2 exponential of minus t. All right. Then we want to plot the phase plane for this and for this systems. Even though we solve it out, but we want to see whether 0, 0, as you can see, it's called fixed point, is stable or not. Okay. So the way we are going to plot the phase plane. The x-axis is x1. The y-axis is x2. Okay. And then we pick, so obviously this is not as easy as first order problems. And we can see if we plug in any vector, and we can basically generate a vector field. For example, in this case, let's say it's 1 and 1, and we plug in. And we can find out that the vector field at point 1, 1, which in this case becomes 1, 1, 4, 1 times 1, 1, and it becomes 2 and 5. So this 2 and 5 is the vector field. It's called tangent vector. at 1, 1. So basically what does it mean is, say we have a point 1, 1, and we have a tangent vector point that way. Okay, so this tangent vector is 2 and 5. And this position is 1 and 1. Of course, you can apply and you can find more arrows, probably something like that, and something like that. And for each point, you can find out such kind of tangent vector, and you can plot this out. But obviously, this is not very handy for like human being to plot all these arrows. So the way that we do is we just leave it to the computer softwares. And in the problems, I mean, in the course website, there's some software called ppplane, and basically it will plot this tangent vector for you. And let's do that together. Okay, so this is basically the interface that you will see. And obviously, in this case, we are using x1 and x2. But I mean, in the software, and we are using x and y. But I mean, basically, it's the same thing. And we can transfer from the vector into x and y, and this becomes x plus y. And this becomes 4 times x plus y. Of course, the most important thing right here, and we need to set up, the domain. We want to set a domain that we are interested. So keep in mind, we want to see the 0, 0 is stable or not. So definitely, the domain has to include 0 and 0. So let's make it say the domain is from -2 to 2 in the x-axis and -2 to 2 in the y-axis, which basically is a cubic. So let's proceed. So yes, so this is basically the arrows that I draw, and this program, well, what they do is pick each point and find out the tangent vectors, and they plot the tangent vectors on each point. So that's basically how it looks like. So it's very handy and nice, in fact. And with the help of this tangent vector, turns out we can plot the solutions. For example, if you are given some initial conditions, say I'm giving the initial conditions right here, then what you do is you click, and this blue line is basically the solutions. And you can see these arrows right here. If you look at the correctly, these arrows will be the tangent line of our solutions. And you can plot more. For example, if I'm giving the initial condition for here, for here, for here, for here, for here, and you can see, can play around with that. So these lines are all solutions, and you can see all these arrows are tangent with our solutions. And there's a fixed point right here, which is 0, 0. You can see this is our fixed point. What we can do is we can find out the equivalent point, and it tells me there's a saddle point at 0, 0. So it tells me this 0, 0 is a saddle point. So the reason it is because of the saddle point is lambda 1 is larger than 0, and the lambda 2 is less than 0. And if we plot that out just one more time, sorry about that, I just accidentally closed that. But let me just do it again. I'm going to put it in the same domain. Okay, so this is the graph. So let's just plot several solutions out. Okay, so this is basically the solutions. And so the reason that is saddle point is our so the first eigenvalue is larger than 0, and the second eigenvalue is less than 0. And basically we have one term, and which is grows exponentially, and another term, yes, that decays exponentially. And turns out if we saw some points, for example, I'm starting right here, and which is a little bit far away from 0, 0. And you can see we will approach 0 closely, then we will leave away 0, 0, and it goes to infinities. So for this solution, we will getting closer, closer, closer to 0. Then we make a turn, and we will goes to infinities, drop out. And also this also works like this. And we're getting closer, then we are bouncing out. We're getting closer, then we are bouncing out. So as you can see, for the long time behavior for this xt, can be positive infinities or negative infinities. Depends on which part of your settings. So obviously this is unstable. Okay. But there's a special name for this kind of unstable. It's called saddle point, because one of our eigenvalue is larger than 0, and one of eigenvalue is less than 0. And in some trend, we will basically approach basically approach it to 0. But in some trend, it will, and the solution will goes away to 0. Will goes away from zeros. Okay, so this is basically the plot. That we did for the phase plane. But sometimes you don't have the, for example, you don't have the way that the MATLAB helps you. So the way that we can do is we can basically sketch the solutions out by hand. So how we are going to sketch that by hand? Okay. So let's say, and let's forget about this. But we know this is our solutions. Right? And for example, I trying to pick some initial condition such that C1 is equal to 0, but C2 is equal to 1. On that cases, our xt will becomes C2 of exponential minus t minus 2 exponential of minus t. And we know this is x1 and x2, right? So turns out that we can write down our solution by simply using this this x1 and x2. It's very simple. It is x1 times minus 2, well, it becomes x2. So right, so in fact, if we draw this picture in right here, it is basically a straight line. It is like that. It turns out that this is one of our solutions. And the solution, as we can see, when t goes to infinity, it will go to 0. So that means it will go to 0. Right? I mean, makes sense? Then let's see the second cases. I don't have enough space. Let me just erase this part. Well, this is pretty hard to erase. It's a little bit work. All right, so let's take the second cases, which let's say we find out some initial conditions such that to make the C1 equal to 1 and the C2 equal to 0. And now in these cases, our C1, x1, x2 will become C1 times exponential of 3t of 2 exponential of 3t. Okay? And if we write down the solution as a function of x1 and x2, that would give me x1 times 2 well, becomes x2. Okay? This again is it's a linear function. So if we plot that, this is something like this. And as t goes to infinities, this vector will goes to either positive infinities or negative infinities, and it depends on the signs of C1. So it goes to positive infinities or the right? So we know this is like two very straightforward solutions. And how about other solutions with other initial conditions? Wow, it's kind of annoying. So we will basically interpret other solutions by, with the help of these two lines. So we just draw some functions sort of close to these two solutions. And we wish when the solution is very close to these two lines and they behave similarly. So obviously, the solution is roughly looks like that. Hopefully, we can verify this from our PP planes. Well, this is not very perfect, but let me just shrink a little bit. And you can see, roughly, you can see this one solution that passing 0. It's not very perfect. Let me just make it a little bit. And you can see the solution is basically very close to these lines. Right? And oops. Okay. And there's also one solutions along these lines as well. Okay. So basically, so one line's on this one line's on this, and which corresponding to this and these two straight lines. And you can see the behavior of this solution is very similar to what I write down right here. Okay. So what you can do is you can using PP plane to generate this figures for you, or you can using what I have to interpret and to write down this basic ideas of this, what is called face portrait, or the face portrait, or the face planes of this. But for these cases, we don't have arrows, and I just plot some sample trajectory solutions like this, and every trajectories right here is corresponding to one of the solutions. If I want to plot out these arrows, and each arrows at this will be the tangent vectors of that. Okay, but it is too messy. I don't want to plot this. These are all tangent vectors of that. Okay. If you want to see the vector field, the better way is you go to the PP plane 8, and they work pretty much perfect.